and share a presentation. Okay, just a second. So we looked at indistinguishability of encryption and PRGs and stream cipher construction, and we want to go beyond this. The mechanism that will allow us basically to go beyond this is something called block cipher. Wait, oh, sorry. But first I wanted to motivate it. So I was like, I want to start with block ciphers? No. So the real motivation for block ciphers is that we want to stream cipher. You cannot reuse the key. It's not clear so how to build an encryption where the same key can be used to encrypt many messages. And that's what we need. We'll do that using block ciphers, and we'll see also how to basically construct block cipher from a stream cipher, but that's later. So okay, syntactically, you have an encryption that takes a key and a message and creates a ciphertext. So to reuse the same key, there's no difference in the syntax. But what we need is a new security notion, because the notion, if you remember the picture from last time, where adversary chooses two messages, M0 and M1, sends it to the challenger picks a key and uses it once by encrypting either M0 or M1, adversary gets a single ciphertext, and his goal is to determine whether it's M0 or M1 that were encrypted in this ciphertext C. But that's all he sees. The adversary just sees a single ciphertext. That models a scenario where somebody picks a key and just uses it once and never uses it again, because in that security notion, adversary only got to see a key used once for a single message. It was maybe very long, but it was still just done only once. What it would look like if we wanted to let adversary get the power to see encryptions under the same key of many messages? Well, that's called chosen plaintext attack. Adversary chooses a bunch of messages, sees encryptions of chooses first message, sees an encryption of that, chooses another message, sees an encryption of that. That's exactly plaintext attack. And it seems very strong. Like, why would you allow adversary to see encryptions of arbitrary messages of adversary's choice? It models real life, for example, because there is structure to messages that people send. So people send messages that are PDFs, TCP, IP packets, XML, that is actually very predictable. Moreover, I know what XML you might get because I can interact with the same website and examine the XML. So I know exactly how much of the XML is variable based on some secret data of yours, and how much is very predictable. So if XML document is divided into IP packets, a lot of these IP packets actually I can predict in their entirety as an attacker. That still doesn't mean that I choose them, but at least I know them. But how can we model attacks where adversary knows the plain text but doesn't choose them. Okay, is it that he gets to see encryptions of random messages? So who chooses them if it's not an attacker? I guess your natural thing will be an application chooses them. But what is an application? Who chooses the application? And basically, we say, let adversary choose this application. Let it be the worst application you can think of. Let it be, the XML code is perhaps influenced by adversary's actions. You can try to think of weaker security notions, but they are going to basically fail to model reality adequately in many cases. So therefore, let's just choose a strong notion and go for it. And that notion would imply security under any application, however messed up its choice of messages. And the goal is still the same. It's semantic security, so indistinguishability of some message that adversary doesn't have certainty about. So here is how this would look like. This is one way to specify this generalization of the indistinguishability to the notion that covers multiple usage of the key. The generalization is adversary chooses not a single pair, but many pairs indexed by I, going 1, 2, 3, Q for the number of queries. We call these things an encryption query, where adversary specifies two messages and he gets to see their encryption. Okay, but what does he see encrypted? He sees encryption of one of these two messages. This bit determines which one. So it is a strict generalization, and his goal, adversary's goal, is as before to output a bit. And as before, we are going to say that that the encryption is secure if the advantage in the multi-message version of the CPA game, which is defined as basically correlation between B prime and bit B. So the probability that the output of the purple box is 1, given that the input of the purple box was 0. This is this probability. It's the probability that adversary outputs a fixed flag on if the challenger encrypts uses bit 0, versus the probability that adversary outputs the same flag given that the challenger used bit 1. So you can see that for Q equal 1, this is the notion that we had before, right? Because there's a single pair here of the left and right message. But now his adversary is allowed to see a bunch of these left and right messages. Also, he chooses them after seeing the ciphertext. So he's free to send a message pair, get to see ciphertext, and then choose a new message based on this one. And for some crypto systems, it's going to be an important difference. And in some applications were broken because people didn't realize that what happens in reality is that attacker can see the ciphertext and base new messages based on the ciphertext they see. But what adversary's view is, if bit is 0, then what he sees here are encryptions of always left messages. And if this bit 1 is, he sees encryptions of right messages. That's why it is called left or right security. Note that this corresponds to a chosen plain text attack because if adversary wants to look, these ciphertext, adversary sort of doesn't know ever what exactly these ciphertexts are, because they can be either encryptions of left or right. However, if he does want to see for sure an encryption of some message, he just makes one of these pairs in such a way that the left and the right are the same. And then he knows exactly what the ciphertext is of, because it's independent of this bit if the two messages are the same, right? So it captures chosen plain text attack, but it basically what it captures is that you get to see a traffic, okay, encrypted traffic. And the encrypted traffic might correspond to these, let's say students' messages, which are formed in a certain way, or professors' messages, which are formed in a different way. You don't know which ones are there. You know that, like, if he was a student, his first message would be this, and if he was a professor, the first message would be that. This is your first MI0, MI1 pair. And perhaps the next message from student distribution would look like this, and from professor distribution this. That's your next pair. Perhaps the two are the same on a bunch of XML IP packets that encode XML that does not differ. Well, on those ones, you make the two messages the same. You're just so you either see consistently students type of messages or professors type of messages, and your job is to determine which ones are those, right? Which case you are in. Here is another view of CPA security, which okay, depends on your taste. You might find either easier or harder to see, but anyway, it's an alternative view. Adversary, so the challenger has this secret bit and chooses a key. So far it's the same, but instead of sending a pair, adversary sends only single messages and gets to see their encryptions. Then at some point he decides on a single pair. Unlike in the previous picture, it's not always pairs, but at some point there is a pair. These are called challenge messages. So these are referred to as chosen plain text attack queries. These are referred to as encryption challenge query. So M0 star, M1 star. And these are now finally this bit B is in operation. Just like in the indistinguishability notion, he gets a ciphertext, which is an encryption of either this or that. And the chosen plain text attack queries continue. So he can specify new messages and gets to see their encryptions again. At the end, he has to output the bit as before. Okay, and we define security in the same way. Do I have a slide on? It will be a homework exercise to show that these two models are equivalent, that these two notions are equivalent. It is easy in one direction and not so easy in the other. So I already basically alluded like one direction is easy because I explained on the previous slide that the multi-message security, so-called left or right security, basically this interaction is a special case of the left or right. It's a special case where in all Q queries here, the left and the right were the same. And for these queries from Q+1 to Q prime, again, left and right were the same. The only pair that differed is this one. So this is a special case of the other attacker. And that fact, if you think about it, makes one of these, the implication between these two notions, one direction, very easy. The other direction needs some gymnastics to do. Okay. But you know, right now, for example, you can think like, okay, which of these is strong, is sort of intuitively stronger, but then they turn out to be equivalent. I see there are some messages on the chat, so I will just check. Somebody says, hold on. Emily, you are asking the basis nearby to practice a little later. What do you mean by that?
Sorry, it was actually not coming from you. Sorry.
Oh, okay. Sorry. Yeah, no, I do have many noises, unfortunately, but hopefully not now. Xiao Chen says it does not imply mi0 mi+1. Oh, you mean? I think what Xiao Chen is saying, do this for every pair of messages I send, the left and the right have to be the same size. So think of yeah, okay. So the professors and the students' message have to be the same size, or otherwise, basically, I would determine between them which one is encrypted by looking at the size of the ciphertext. So we don't ask encryption to hide the size of the message. So therefore, if the two challenge messages are different size, that's unfair. You should be able to tell between, you know, somebody encrypting a kilobyte versus somebody encrypting 2 kilobytes worth of plain text. But as long as they encrypt the same size messages, you should have no clue which message was encrypted. Okay. All right. So we leave this as an exercise. This equivalence between these two models. So here is that a simple example that every encryption that we have seen, and we've basically seen two, which is one-time pad and a stream cipher, is insecure against this notion. And the reason that it's insecure is because it's deterministic. So remember at the very beginning, we talked like, okay, is encryption randomized or is it deterministic? Well, it was deterministic up to now, and it won't be from now on, because you cannot achieve this type of security with the deterministic encryption. So here is why. Let's say that encryption is deterministic, like stream cipher on one-time pad. Let adversary now, let's use this left or right version of the notion. He sends a pair where both are equal, so therefore he gets back encryption of M0, right? Because it doesn't matter whether this guy's bit is 0 or 1, the left and right messages are the same. And now he chooses two messages. So the two messages are M0 is the same one as here, and M1 is new. But M1 has to be the same size as M0. Now adversary sees an encryption of message pointed by index B. But he simply compressed these two ciphertexts, and if they are the same, output 0. And if they're not the same, then output 1, right? And it is a perfect attack, because if encryption is deterministic, C is guaranteed to be equal to C0 if B was 0. And by correctness of decryption, also if B is 1, then this ciphertext must be different from C0, right? So otherwise, there will be no correct decryption. So advantage of this attacker is 1. It's like a perfect attack. this basically shows that deterministic encryption is hopeless and stream cipher is hopeless for this type of thing. Now, so encryption must be randomized. And here is pictorially what a randomized algorithm does. So an encryption with a fixed key, because key is chosen once in this experiment. It is chosen at random, but once it is chosen, it's fixed, and it will be the same key operated in all cases, right? So that's also important to differentiate. Okay, when we mean randomized encryption, we mean in addition to whatever entropy is in the inputs, the key and the plaintext, it has its own local randomness that it applies, it uses. You have seen this, in the last homework problem on homework 1, for example, when we looked at these like randomized versions of one-time pad. So an encryption, a randomized encryption, therefore, will, on a fixed message and a fixed key, sample from some space of possible encryptions of that message. Decryption has to reverse this and map every element from this sample set back to M0. So in some sense, it has to cancel out the randomness and throw it out and distill the encrypted message. And these gray sets, which partition the space of ciphertext, have to non-intersect if we want to have perfect correctness. And now, if the randomness is used in like sort of efficient way, so using the randomness, the ciphertext is basically sampled from this space, then if the space is large enough, then the previous attack where adversary says, okay, give me an encryption of M0, and now give me an encryption of either M0 and M1. Well, in this case, that the secret bit is B, this will be a re-encryption of the same message M0, but because the encryption is randomized, the collision should happen actually with negligible probability. It must happen with only negligible probability, or again, it would be insecure. So if the randomness was not strong enough, and this event would still hold with non-negligible probability, it would translate into a non-negligible advantage of this attacker. Okay. So this also explains, because if the encoding of this set of messages, so ciphertext is an encoding of these messages, right, in this orange space. But the orange space for every message will have many ciphertexts. So basically, this set cannot be described with the same number of bits as the messages. And effectively, you have the following bound, that, well, only if the random bits are effectively used, right? Because you can waste randomness by creating collisions here for different, even though you're running with different randomness, you basically collide here, right? So that would be an ineffective usage. If you're using it correctly, you should achieve this. So the ciphertext size is basically the plaintext size plus the randomness. It might be that your ciphertext needs to be larger still, but this is the minimum bound. They cannot be smaller. If they're smaller, then that means that you're not using real randomness correctly, and you are contributing to the collision probability, and therefore contributing to the probability that this event will happen and this attack will be successful. We'll see that this randomness is actually related strictly to the security parameter. We'll see how shortly. Okay, let's just look at the block cipher from oh, Xiaochan is asking whether messages in this attack have to be the same size. No. You can ask first, the student and the professor both encrypt the short message, and then they both encrypt the long one. Okay, this will be our warhorse to handle security for key reuse. So what is the block cipher? It is a pair of algorithms, encrypt and decrypt. The encryption, both of them are keyed, and the encryption takes n bits inputs and outputs n bits outputs. Decryption reverses this. The input here is customarily called plaintext block. Ciphertext, the output is ciphertext block, and for decryption the roles are reversed, right? Because the decryption is not really the perfect picture. Decryption maps from here back to there, given the same key. The block ciphers that are currently common in operation, like triple DES or AES, here are the example parameters. And they have very different parameters. Like, for example, triple DES has twice or more, or 3 times shorter blocks than key bits. AES has twice longer blocks than triple DES. The keys actually could be shorter, but AES specifies 3 different versions of the standard for basically 3 different levels of security, right? So currently it is okay to use this, but if you want to have stronger security for future sake, you can use higher key lengths as well. The inside of the block cipher is we will come back to this, but let's just flash this picture for now. The way block ciphers typically work is that given a key, they use a key expansion algorithm, which takes this key and basically expands it to create a series of keys. These are called round keys. And it has some round function, which typically have the same circuit. So it's the same function, perhaps with some added tweaks and parameters that differ round by round, but basically they can be conceptualized as additional information in this key expansion. And the round functions use these round keys and successively. So the first round function uses the first key and processes M. This is its output. And then it feeds to the second round function with the key K2, and so on and so forth. The decryption reverses this process. So it creates the same expansion table of keys, and then has a circuitry that inverses R and computes R inverse on this sequence of keys in the other direction. They also differ by how many these round functions they use. And intuitively, triple DES, hold on a second. I'm so sorry. I'm getting a phone call and I have to, yes. I do not know how to switch them off while lecturing. Yeah, no, I should just log out of Gmail entirely, because that will be one way. They have very different number of these round functions. Intuitively, AES round functions are much stronger. So DES uses many more but weaker round functions. Note we will look at what's happening in here soon enough. But let me just say that this blue software, this blue circuit, you already know what that is. This is a PRG. It's a PRG that is applied to key K, and it expands it as a sequence of keys, either 48 or 10, okay, for different ciphers. This circuitry is exactly a PRG, and if it is a secure PRG, then you can think of the key that is used in practice as just a seed that really creates inside, under the hood of the block cipher, n pseudo-random keys, which are as good as if there were n independent random keys. Therefore, the analysis of a block cipher design really should focus on round function and think of these round functions as keyed with independent keys. And that's the beauty of the PRG. It allows you to do that, because once you have confidence in the PRG security, then these keys can, for all purposes, be treated as uniformly created independently. Okay, we'll come back to what's happening under there to implement, in different block cipher design. Now we'll just state what we need of a block cipher. So what is the security notion that we that we require of a block cipher? And there are two security notions. One is called pseudorandom function, and the other pseudorandom permutation. Let's look at the notion of pseudorandom function first, because it's easier. Pseudorandom function takes three spaces: key space, argument space, and value space. And the function is a function that takes two arguments: a key from the key space, a value argument from the argument space, and returns a value from this range. And there must exist an efficient, so polynomial time, deterministic algorithm that evaluates this function. Well, that's similar to a PRG, that it is some function that takes a short seed and creates a much longer pseudorandom string that can be evaluated by an efficient deterministic algorithm. A pseudorandom permutation modifies this as follows. The range is the same as the argument space. This part is the same, but also for every choice of a key from the key space, this E function, index with this key, thought of as just the function on elements in X, is a one-to-one function. In other words, it's a permutation. It's collision free. If you are computed on X1 and computed on X2, they map to two different elements in the range. And not only that, so because the domain and range are the same and it's a one-to-one function, so therefore for every key it's a bijection. So inversion exists, but what we also ask is that not only that the inversion exists, that there is an efficient algorithm called D, which inverses E. Inverses in the following way. So if you, for any K, and any x, if you run E on x, and then you feed it to the D, you get back x, right? So this is the same notion of inversion that we had before of, how decryption inverses encryption. But now it's about deterministic algorithms, okay? It was effectively about deterministic algorithms before because that's all we knew, but the notion is not limited to that. But this one is PRFs, PRPs. Okay, so that's a syntactic, these are syntactic requirements. It must be efficiently computable by deterministic algorithms. And in case of a PRP, there must exist an inverse. So therefore, in particular, for every key K, it's a bijection. Now, what about security? Security will be, the intuition is this. In a security argument, you will be given access to a box which picks a key and which implements either of the two types of functions and chooses the function from this set and this set at random. On the left-hand side, you have a set of all functions that are defined by this PRF. Namely, it's a set of keys, and each key K determines the function. SF is the family of such function, right? Ranging over all key Ks. In here, you have all functions from this domain to the range. And in the security experiment, you will either talk to a random representative of this family, in other words, to a random to a function which is one of these, and is randomly chosen from the set. In other words, this key is chosen at random, and the function is fk. Versus a random function from this set. And what is a random function from this set? It's a random function from domain x to range y. On the left, we call it, if security notion would say no efficient algorithm can distinguish a function from here from a function from here, where he doesn't get the code of the function, he gets a box which computes this function on any inputs. So he doesn't know what's inside the box, because if he could, then he would just open the box and see, this function has a huge table, it's a random function. Or, no, this function has a short circuitry of DES, it's a DES PRF. No, you are only getting a function in a box. So you can specify its argument x, and the function spits out the value y. You can specify another x, get to see y. If the box is one of these, or one of these, no efficient algorithm can tell the difference. That's why so what's on the right-hand side? Random functions. And on the left-hand side are deterministic functions. Deterministic after a random choice of a key. But after was deterministic. And but yet, when you specify, the only thing you can do is specify arguments and see values, then you cannot tell a difference between interacting with such function and interaction with a random function. Therefore, we call those functions pseudo-random functions. And that's the security notion of what a pseudo-random function is. It's sort of similar to a pseudo-random generator, right? It's created this big string. It was not random. It did have a random seed that allowed it to generate, but it was not a random string, and yet it was indistinguishable from one. Hence, we call it a pseudo randomness generator. Now we'll be talking about boxes but PRG in some sense is a one-time use. He gets a seed, he creates an output, and that's it. These things are interactive algorithms. We give them any input, they give us an output. We give them another input, they give us an output, and we can interact with them any number of times we wish. Okay, and we call these pseudorandom functions if interaction with them is indistinguishable from interaction with a completely random function. Here is how this adversary looks pictorially. He chooses an argument and x, and he either talks to a random function or to a PRF. In the random function case, he gets R of x. In the pseudorandom case, he gets fk of x, where k is fixed, although it was randomly chosen at the beginning, but after that, it doesn't change. And he recurses. So he can do it for x prime and see again, either R of x prime or fk with the same k on x prime, and on, right? In all these, if he's talking to a pseudorandom function, key k will be the same on all these answers, and x will be whatever adversary specified for a given PRF query. And it will be secure if you cannot tell a difference. Permutations is the same. The only thing that changes is that here, instead of taking a random function, we take a random permutation. Let's do a following experiment. So you have a random function from domain X to a range of 128-bit strings. And let's say you modify it like this. On key k and input x, you just run f of k with the same key and same argument on all x's except where x is an all zero. It's a zero, in which case you return 128 string of zeros. In other words, you take a PRF and you modify the way it outputs on a single x by just hardwiring the output to be this value independent of the key. No matter what key, right? He will just output this on x equals 0. And my question is it easy to distinguish this from a random function? So let's say f was a secure PRF. So if somebody chooses k at random, no matter what x's I query, what I choose, adversary chooses, when he gets fk of x, he cannot tell this from random. What about g, the modified f? Would it still be secure in this sense? Or is there some test that will distinguish a random gk, so a random function g with a random key k from a true random function?
Is the key fixed, or the input of G is 2-bit strings and bit strings?
The key is fixed throughout execution, but it is fixed at the beginning. So in all security experiments we have seen, the key is chosen at random at the beginning, and then it stays constant. So for example, in a multi-message security notion, key is chosen at random, but after it's chosen, adversary gets to query a bunch of messages, and it's always the same key that is used. In the PRF security, key is chosen at random, but after it is chosen, adversary will ask, give me the value of fk on x1, and he will get fk on x1, but now give it to me on x2. He will get fk of x2. K will be the same, xi's will change, but key remains the same. But actually here it doesn't matter, because it's sort of, even if you could query this once,
Yeah, I mean the input to G, because if you are doing the PRG experiment, the input of G is not controlled, right? It's random. So the randomness is going to K and X or just X?
No, I don't know what you mean by input is not controlled. No, input is controlled. Adversary determines, for example, X. Adversary determines the axis on which this hardware will execute. Okay, you know what? Maybe a picture will be better. Okay, do you guys see my my board? What is bigger, the board or the slide? Do you see a small board and a small board and a big slide, or a small slide and a big board?
I see a small board.
Okay. And now it's a large board, right?
Yeah. Yeah.
Okay.
Yes, so a PRF, it can be a PRF because 0 would always go to 0, right?
Yes. So here is an experiment. A sends so A talks to either fk, where my notation for fk of x is fkx. By sending any argument, and it gets back yi, which is fk of xi. But at the beginning of this experiment, k was chosen at random from the key space. Okay, so this is the first step, and then all of this is happening, right? And adversary wants to output a bit. So this is case 1. A talks to a PRF. Case 2 is A talks to a random function. And here it's like this. We pick function R as a random function from all functions from domain X to domain Y. This is the first thing. Then adversary can ask his queries, and what he gets back is values of this function at the arguments he asked for, and he outputs a bit. We say that PRF, that fk is a secure PRF, or F really is a secure PRF if for all efficient A's, the probability that B prime is 1 in case 1 minus probability that this bit is 1 in case 2 is negligible. Okay, this probability goes over random choice of key and randomness of A, because A is randomized. Perhaps it chooses excites in some randomized way. And of course, there was a randomness in this initial choice. After that, there is no further randomness in here. Okay, this is a deterministic function. And here, it goes over random choice of R, the true random function, and randomness of A. We draw it as if A, has two different conversations. Of course, A doesn't know which case it is faced with. That's precisely the goal of A, to determine, to output this bit in some way that is different. In the case it's talking to a random function, in the case it's talking to F. Okay, so now, what was the example on the slide? It was that F prime at X all zeros, 0 was forced to be an all zero string. And for all X different from 0, F prime Kx was just F of Kx. Right? So now, what did you say, Bruno? Yeah.
That it couldn't take 0 to always 0, because then you can check it.
So you being adversary.
Yes.
Right.
Yeah, the problem before was that I misread your question.
Right. So adversary can, exactly, he can query here as 0. And what's the test? The test is that output bit B equal 1 if the value here is exactly that one, right? All zero string. The probability that he outputs 1 when talking to this F prime is going to be 1, because it doesn't matter what key is chosen. This function will always return the string when you ask it on X equal 0. And what's the probability that the same is true for a random function? Well, it's the probability that a random function maps 0 onto this string. Well, it's maybe important to say, what is a random function? Random function is a map that for every argument, how long is this table? As long as there is number of arguments in the size of the domain. It picks these completely at random from the range. So y1, the value of the function at x1, is a random element. y2 is also a random element, and so forth. Each of them is random and independent. So that's a random function. The values are independent of each other, and each of them is sampled at random. So the value of this argument is a random 128-bit string. So the probability that, the probability that basically in this case, it will be 2 to the minus 128 probability, and here the probability will be 1. Another thing about these random functions is that, hold on, let me focus. random functions have no short description. So they cannot be evaluated by an efficient algorithm at all. I mean, okay, so I cannot describe them succinctly, right? Because let's say that X and Y are both n-bit strings. So here are all the here's the function r from X to Y. How many arguments I have? 2 to the n. How many possible values? I mean, well, each one has n bits. These bits, which is the value of the function at, let's say I start with an all 0 and end with a 1, 1, 1, right? And I have all 2 to the n possibilities in between. This thing is r at all 0, and this thing is r at 1n. And this, every, you know, here I have some x, here I have r of x. Each of them, this is basically an n by 2 to the n sized random table of random bits. So every table of this size will define a different function. So the functions are one-to-one with such tables. To choose a random function means to choose a random table. And it's right here that you see that these tables have exponential size. Okay. So I cannot really, if I'm talking to a box and I'm giving an X and it outputs a Y, well, if I could measure the size of this box and see that it cannot have this many bits, then I would always say, you know, a box too small. F is a PRF, not a random function. Yeah, but this is outside of the model. I mean, this is a intellectual, you know, this is just a mental experiment that an attacker gets to see a box. In real life, he never gets to see either a real function or a random function, because random functions sort of don't exist. They're too big in real life. So what everybody sees in real life are the PRFs. The point of the mental experiment is to show that, well, if no efficient adversary can distinguish between a PRF and a real random function in its input-output behavior, then the usage of this inside of the encryption algorithm perhaps has some beneficial properties, as we'll see shortly. A good way to think of a random function is a stateful table. So in security experiments, we need to think of these random functions in some way. Well, the way we will think of them is like this. Let A send the first argument. So it is somewhere here in this table. We will fill this with random bits. So this will be chosen at random from the you know, the appropriate range, and then we'll fix it. So maybe a better way to say is that at that point I'm choosing Y1 at random from the range, and I'm writing Y1 in my table. so that the next time, if adversary asks for the same on the same argument, well, I already have it written here, so I return. If he sends a new argument, I do now at the new point, I choose this value completely at random, and I write it here. Right? So I populate this table as he asks me inputs. He will ask polynomially many times. So I will only do this polynomially many times. It doesn't matter that this whole table is exponentially sized. I will never have to fill in all these spaces. So in that sense, the random function can be modeled by a small stateful algorithm I just described. It's a randomized small stateful algorithm. Okay. Hopefully this gives you more intuition about what the random function is, what the pseudo-random experiment is all about. Okay, right. So that was the answer indeed. Here is the view of these notions using the same kind of definition like we did in for PRP, for PRG, for indistinguishable encryption, etc. So adversary is on the right side, and then there is a secret bit. If the secret bit of the challenger is 0, then the challenger picks a random key and instantiates function f as a PRF with key k. If the challenge is 1, then he instantiates the PRF as a random function. Sorry, it's f, little f, as a random function. And after this initialization, adversary can ask queries, and he gets values of little f. The little f looks like this if b 0, or it was chosen from this distribution if this bit was 1. But it is fixed after initialization. Adversary can ask another query, he gets the value of the function, etc. And his goal is to output, and we say, as before, that his judgment should be uncorrelated with the secret bit. So that's the way to view it. Now you see that all the randomness in the key was sort of before the experiment started, and in this case, all the randomness choosing of the function was also before the randomness started. What I just showed on a piece of paper is that you can, in this case, you can equivalently think of these values chosen at random every time. Okay, because it's just an equivalent view of what it means for a random function to be chosen. Okay, and this is what models what I was saying at the beginning, that A either talks to a box that implements a PRF on a random key, or it talks to a box that implements a random function. And the F is a PRF, secure PRF, if no efficient test can distinguish between the two. If this one, in the case of a PRP, not much changes in this notion. It's just that in the ideal case, though I will use words like real and ideal. Real is what is the B0 case. This is the real world, where like in the real world, the functions adversary will talk to will be some cipher, some PRF. But in the ideal world, we're going to model this as if it was a random function. For in the PRP case, in the ideal world, we'll model this as if it was a totally random permutation, right? Not a function from X to some other, well, but a permutation on the domain. here's a technical thing that shows that we often, well, that sometimes it does not matter whether it's a PRF or a PRP. Because if the domain is sufficiently large, then okay. So here is the thing. If you look at the block ciphers that we introduced, like triple DES or AES, the domain and range are actually the same. And and the inverse always exists. So therefore, these in the real world, these machines, they implement not just functions, they implement permutations. So shouldn't you always compare them in the ideal world to random permutations? Why do you even consider this case? Because block ciphers are, okay, they're functions, but they're very particular functions, they're permutations. So why do we bother with this notion of a PRF as a valid way to analyze block ciphers? Because if the domain is sufficiently long, then it does not matter whether we view them as, in the idealized world, as random functions or random permutations. And here is the reason why. The reason why is that for any adversary A that asks Q queries, if you measure his advantage of between in distinguishing some block cipher E from a random function, and then you measured the advantage of adversary E distinguishing the same block cipher not from a random function but from a random permutation, then the difference between these two is bounded like this: square of number of queries over the domain size. Why is this? So let me just show that what are this is basically the birthday probability. So let's skip this for a second and just believe it for a second. We'll come back. The consequences of this is that because the difference of them, this entity, if Q is polynomial, then this entity is negligible. Okay, if the domain is sufficiently large, so the domain is exponential size in the security parameter. So think of domain here as just n bit strings. Okay, then there's 2 to the n elements in it. Then no matter what this Q is, it's a polynomial, so its square is a polynomial as well. Okay, so therefore, if one of them is negligible, then so is the other, because the difference between them is negligible. Now, why is this equation, this inequality true? Let me just go back to the here's the explanation. Okay, I said that the advantage of this attacker against sorry, in the PRF notion of attacker E against the block cipher E minus advantage in the PRP notion, that they are bound by Q square over X. Okay, let P be the probability that A outputs 1 if A talks to ek, and the probability goes over random k and randomness of a. Let p prime, the probability that a outputs 1 if a talks to a random function. And p double prime, the probability that a outputs 1 if it talks to a random permutation. Hold on, let me make sure that I don't draw over the board. So this quantity is p minus p prime. This quantity, it's p minus p double prime. And the difference between p prime, if I compare it to p minus p double prime, is upper bounded by the difference between p prime and p double prime. Right? It doesn't matter what p is, it's going to cancel out. And this is the upper bound on the difference between how far p and p prime can be versus p and double prime, p and p double prime. So that's the only thing I have to upper bound. And what is this upper bound? It's the probable. It's how good can a. So you see, right here, it's just about differentiating between random function and random permutation. E vanished. It's no longer even in the picture. How can a who sends messages to a random function and gets it right, and he can recurse? How can it differentiate between sending values where r is chosen at random from all functions from x to x versus he talks to a random permutation and p is chosen at random from all permutations on x? There is one event and one event only that can allow you to distinguish this from these two cases. Can anybody see what they are? So in this case, on any x, you get back a random function. So you're talking to a random function, to a random table, right? Zero the x's and y's. You send some x, you get back a completely random value here. You send another x, you're sending a completely random value here, etc. In here, what is the difference? Are these completely random values, or is there some constraint that has to be maintained for this to be a random permutation? Exactly, right? So the event is, the event E is that there exists x and x prime such that this r of x collided with r of x prime, right? So you can this is the only test an adversary can do to distinguish a random function from a random permutation. And therefore, so if you convince yourself that this is the only test, then you can just measure the probability that this will happen. Adversary asks Q of these queries, and each of them is a random value from the n bits. What's the probability of ever encountering collision? And that's exactly the birthday bound is the square of the number of queries divided over the size of the space, which is this. Yeah, this is what we claimed, right? So it's equal to q squared 2 to the n if x is n-bit strings. An equivalent view of why this is the skew between these two distributions, basically this and this, is that permutation is effectively, there is a constraint, right? That each of these is chosen. Not the first one is chosen at random, but the next one is chosen at random, except it has to be different from the previously seen one. And now this is this algorithm will, you can convince yourself this is exactly talking to random permutation. It's a stateful machine that picks the first one at random, and the next ones it's chosen at random from the reduced space that you kick out the previous ones. You can think of this random function as saying, okay, it will emulate the permutation if it introduced the same constraint. The probability that the constraint would be in operation is this. This is the probability that without, that you will violate this constraint that is imposed by a random permutation. Okay, so it is not just that the test like this exists, it is the only test possible. Without this event, these two will have the same distribution. So it's an information theoretic distance between these two probability ensembles. Okay, what does this mean in practice? Why do we care about this switching lemma? Because let me check if I have it on the slide. No, so this is, yes, it is negligible asymptotically, but in practice these values might actually be significant. For example, think of death. It has, the outputs are only 64-bit long. So the space here is 2 to the 64. That means that already with Q equal 2 to the 32, this is the same as that. So this bound is basically meaningless for in the case of death. Already when Q is just 2 to the 32. 2 to the 32 is, 4 billion. And 4 billion is not that much, right? So if you have whatever, some VPN or whatever server that uses SSL, you might get to this number of IP packets or blocks that are transferred using a block cipher. And at that point, the fact that it is asymptotically negligible, it actually it's meaningful and useful to remember what the actual amounts involved are, because it will sometimes be very important whether a function model is a PRF or a PRP. The importance will be reflected in these terms, and for some ciphers which have not enough block size, this will actually be have practical consequences. Okay. I think this is a good place to stop, because the next topic is like using block ciphers and then constructing block ciphers. So maybe we should postpone this till the next time. Is there questions on this? Oh, I see Bruno has some link to some paper with a switching lemma details. Okay. Okay, so if there are no questions, then I will see you on Wednesday. Bye everyone.